This unit talks about chemical bonding and how different chemical bonds form different types of compounds, and then we're going to go into how to name those compounds and how to write formulas for those compounds. So we know that elements combine to form compounds. These compounds have different properties from the elements that make them up. Atoms of different elements are held together by what we call chemical bonds, and these bonds determine the properties that a compound has. For example, these properties depend on atoms that are in the compound and on how the atoms are arranged in that compound. For example, carbon and hydrogen combine to form the natural gas, automobile gas, waxes and candles, and plastics. Properties of compounds are different than the elements that make them. For example, water, H2O. Hydrogen and oxygen are both colorless gases at room temperature, but water is a liquid at room temperature. And another example we know of is salt, NaCl. Sodium is a metallic solid, it's actually silver in color, and chlorine is a greenish-yellow poisonous gas. But when these two things combine through chemical bonding, they form table salt, which we use in every single everyday food to flavor them and to preserve them. We know that atoms combine in predictable numbers. Any given compound always contains atoms of elements in a specific ratio. For example, ammonia, which is a cleaning product. Ammonia has 1 nitrogen atom for every 3 hydrogen atoms, and that is the ratio, 1:3. Chemical formulas are a way to write out that ratio. They use the chemical symbols for the atoms that are in the chemical formula or the compound and the ratio that they're found in. For example, H2O has 2 hydrogens to every 1 oxygen. So to form these compounds, we have to talk about different types of chemical bonding. Chemical bonds are the glue that hold the atoms of different elements together. They form when the electrons in the electron clouds interact with each other. So if you have 2 atoms that interact with each other and end up sticking together, that stuck togetherness is formed from chemical bonding that happens between the electrons of the 2 atoms. We know that atoms can transfer electrons. When we have ions that are formed when an atom gains or loses electrons, we know that gaining electrons gives the atom a negative charge because it's adding negatives to the overall atom, and losing electrons gives the atom a positive charge because we're taking away some negatives, making the positive charge bigger. And those ions then are used to form bonds. An element's location on the periodic table gives us a clue as to the type of ions the atom of that element will form. Group 1 metals, we know these are highly reactive. They usually lose 1 electron to form positive ions. Group 2 metals also form positive ions. They are usually losing 2 electrons. Group 7, which remember, group 7 is found after the transition metals, they gain 1 electron to form ions with a -1 charge, so they're forming negative ions. And group 6 nonmetals do the same, but they're gaining 2 electrons, so they have a -2 charge. So things on the right side of the periodic table are positive ions. Things on the left side are positive ions. Things on the right side are negative ions. So if we take a look here, elements formed in these 2, sometimes 3 groups, those are going to form your positive ions, and then things over here are going to form your negative ions, with the exception of group 8, because remember, group 8 has a full valence shell, so they don't form ions. Group 1 is losing 1 electron, group 2 is losing 2 electrons, and then we move over here to group 7 and group 6. and so on. These things in the middle, they can lose a variable number of electrons or gain a variable number of electrons, so we have special rules for them. So once we have these ions that are out there roaming around, they form ionic bonds. So when you have ions, you're forming an ionic bond. There is this attractive force between these positive and negative ions. You can think of two magnets that pull toward each other as a similar type of example, although it's not the same kind of force. Particles with opposite electrical charges attract each other, just like opposite poles of magnets, the north pole and the south pole of two magnets, would attract each other. Atoms from elements in group 1 combine with atoms from elements in group 7 to form an ion. For example, sodium combines with chlorine. Sodium loses one electron and chlorine gains that electron, creating an ionic bond and a neutral compound. Ionic bonds form between all nearby ions of opposite charge. So if there is an ion nearby that has the right number of opposite charges, an ionic bond will be formed. These are extremely stable and their crystals are very strong. If you think about table salt, it is made of crystals. If you look at table salt under a microscope, you see a crystalline square or cube shaped structure, and these are very strong bonds. The shape of the crystals formed depends on the ratio of positive to negative ions and the sizes of those ions. So when we name ionic compounds, and we'll get into this a little bit more later, when we name these, you first take the name of the positive metal element, so looking at the left side of the periodic table, and then you take the name of the negative non-metal element and you add IDE to the end of that name. And then you combine those two things. For example, Bai2 would be barium, that's the positive metal element, and iodine becomes, we drop off the ending and add "ide," becomes iodide, so the name of this compound is barium iodide. So naming ionic compounds with the group 1 and 2 added to the group 6 and 7, those are very easy to name. So that's the ionic bonding. Now we've got covalent bonding. This happens between different types of elements. And in this case, the electrons are shared between the two atoms. Co meaning having a partner. So neither atom actually gains or loses an electron like they do with ionic bonding. The shared electrons are attracted to both positively charged nuclei. So really the electrons are being attracted to the nucleus of the partnered element. The nucleus has a positive charge because of its protons. And a covalent bond is represented, when we draw this out, by a line, sometimes more than one line, 2 lines, 3 lines, even 4 lines, between the two atoms. For example, iodine always shows up in pairs of atoms. It's called an iodine molecule. So we write that covalent bond as an I with a line connected to another I. This means there is one bond between one electron pair. The number of covalent bonds that an atom can form depends on the number of electrons that it has available for sharing. So that means it depends on its number of valence electrons. Atoms of group 6, such as oxygen and sulfur, can form 2 covalent bonds. Atoms of group 5, such as nitrogen and phosphorus, can form 3. Atoms of group 4, carbon, silicon, and so on, can form 4 bonds. And in covalent bonding, we're bonding 2 nonmetals together, not a metal and a nonmetal like ionic bonding. So let's look at how valence electrons play into this. These are the electrons in the outer electron cloud. They orbit in shells. You know, our first shell can hold 2 electrons, second shell 8, third shell 8, but all the way up to 18 depending on the element, 32, 50, and so on. We usually only work with 3 valence shells. The quick way to determine the number of valence electrons is to look at which group it's in. We know the group is the column in the periodic table. Group 1 has 1 valence electron, and so on. When we find these, this gives us an idea of how many bonds we'll be able to use in covalent bonding. For example, sodium has an atomic number of 11, so that means it has 11 protons, and it would have 11 electrons in a neutral atom. The electrons are arranged as follows. In the first shell we have 2 electrons, that's the maximum it can hold. In the second shell we have 8 electrons, so we're up to 10 total, and that means in the third shell we have 1, that final electron. So sodium has 1 valence electron, and it's in group 1. So we've looked at ionic bonding and covalent bonding, and we realized that all materials are given their structure based on their chemical bonds. So ionic compounds, these are formed from gaining or losing electrons. Most of these have a crystalline structure. They're solid at room temperature. They have high melting and boiling points, which means it takes a lot of energy to break this ionic bond. They are hard, they're brittle, and they're good conductors of electricity once the ions are separated. And they dissolve easily in water, which is one way to separate ions. Think of NaCl, or table salt. When you have salt water, that's a good conductor of electricity. Covalent bonds, this is when we're sharing these valence electrons because they're equally pulled toward the opposite nucleus. These exist as individual molecules. Chemical bonds give each molecule a specific three-dimensional shape, and that molecular shape affects the properties of the compound. They have lower melting point and boiling points because it takes less energy to break these bonds, since they're organized as individual molecules. And our final type of bonding is metallic bonding. These metallic bonds are defined as the equal sharing of electrons in all directions. So electrons can move easily among the atoms of any metal. Basically, whenever there are atoms of a metal together, they all share electrons. These atoms can slide past one another in metallic bonds, which allows metals to be easily shaped. This is what gives them their ductile properties, meaning they can be drawn out into a wire. It's what gives them their malleable properties, meaning they can be bent and shaped, and luster as well. Metals are extremely good conductors of electric current. They have a high melting point. They're solid at room temperature with the exception of mercury, and they're easily shaped and pounded. So if you have any questions about chemical bonds, please send me a message.